Ever feel like high school geometry? It was like just the tip of the iceberg.
Mm-hmm.
Today we're diving into this research paper, Relative Poincaré Duality in Non-Archimedean Geometry.
Okay.
And I know, it's a mouthful.
It's a mouthful.
But trust me, this is going to get really interesting.
Yeah.
Because we're talking about a whole different type of geometry with implications that could reach as far as things like cryptography and theoretical physics.
Yeah.
What's fascinating to me about this paper, at least from like the get-go, is it's not just like presenting kind of abstract theories.
Right.
It's actually like tackling some long-standing conjectures, offers some new tools for researchers even.
Yeah.
And it even like suggests some potential real-world applications for this stuff.
Yeah. And I think what's so interesting about this is that often when we're talking about things like theoretical math, it can be really difficult to see how those applications might shake out.
Right.
And this paper kind of gives us a little bit of a clearer view into that.
Yeah.
So it's really exciting.
So I guess to start, let's start with the basics.
Okay.
And that is non-Archimedean fields.
Mm-hmm.
What are they?
Okay.
How do they upend everything that we thought we knew about geometry?
Okay, so imagine a world where you could draw a line between 2 points, right?
Right.
And then you could find infinitely many points between those 2 points.
Okay.
That's kind of the space that we're working in. It's like very mind-bendy in that way.
Okay.
That's non-Archimedean geometry. And the usual rules, like you think about high school geometry, you have things like the triangle inequality.
Right.
They just don't hold here.
Yeah.
And so we're really working in a different space with different rules.
So it's not just about triangles with weird angles anymore.
Yeah, exactly.
We're talking about like a fundamental shift in how we understand distance and space itself.
Exactly.
Yeah.
And so this is where this idea of what's called rigid analytic spaces comes in. And you can think of this as like the building blocks of this new geometry. So analogous to like lines and curves and Euclidean space.
Okay.
It's kind of like the building blocks.
So if we imagine ourselves building something in this non-Archimedean world, these rigid analytic spaces would be like our Legos.
That's a great analogy. Yeah. So we can stick them together, but here's the catch.
Okay.
They have very particular ways that they can and cannot stick together.
Interesting.
And that actually leads to this inherent rigidity in these structures that we build.
Interesting. Okay, so what kind of consequences are we talking about?
So one really interesting consequence of this is that it allows mathematicians to define this concept of a boundary.
Okay.
Even in spaces that, from our usual perspective, like wouldn't have boundaries.
Okay, so boundaries without boundaries.
Yeah.
This is definitely stretching my brain a little bit.
Yeah.
But it sounds like these rigid analytic spaces, they're crucial for understanding how anything works.
Absolutely.
In this non-Archimedean world.
Yeah. And so then the paper takes it a step further and starts to talk about this idea of Poincaré duality within these spaces.
Yeah.
So imagine if you had a mirror that not only reflected your image, but it also revealed like the hidden structure of everything around you.
Interesting.
That's kind of the power of duality in mathematics.
So it's like gaining X-ray vision into the very fabric of these spaces.
Exactly, yeah.
And uncovering the relationships and patterns that would otherwise remain hidden.
Exactly, and that's what this paper achieves. It proves new duality theorems for these rigid analytic spaces, and that's a huge deal because it could revolutionize how we study their properties.
Okay.
And it just opens up this whole new avenue for mathematical exploration.
This is where my brain starts to hurt a little, but in a good way.
Mm-hmm.
Before we get too far down this rabbit hole, I kind of want to zoom in on one specific element from the paper, and that's this idea of curve-like affinoid fields.
Okay.
And the paper really highlights these as being really important for describing these non-Archimedean curves.
Yeah. So think of them kind of like signposts at the boundaries of these spaces.
Yeah.
So they help us understand how things behave at the very edge of what we thought was possible.
Okay.
They're crucial for understanding how functions and equations work in this world.
So it's like trying to write the rules of physics at the edge of a black hole.
Yeah.
Except in this case, instead of physics, we're dealing with like the very fabric of space and shape as defined by these curve-like affinoid fields.
Exactly.
Okay.
And the paper takes it even a step further and says, well, how is size and distance redefined in this context?
Right, right.
And that's where these terms like residue fields and valuations become so important. They're like essential for navigating this new landscape.
So it's like realizing that the ruler you've been using your whole life has a completely different set of markings.
Yes.
In this world.
Yeah, and that's what's so exciting.
Yeah.
Because now we can ask all these new questions that we couldn't have even imagined before.
Right.
And explore all these new relationships.
I'm already starting to see how this paper is pushing the boundaries of what we thought we knew about geometry.
Yeah, absolutely.
But I will say there are a few terms that are kind of sprinkled throughout this paper that I'll admit sound a little intimidating.
Okay, yeah.
Terms like henselization and perfectoid spaces.
Okay.
What's the deal with those?
So you can think of those as like sophisticated tools that mathematicians use.
Okay.
So henselization is a way of simplifying these complex structures
Okay.
by focusing on their local properties.
Okay.
So it's kind of like using a magnifying glass to study a really intricate pattern.
Okay.
You're really zooming in on one part to try to understand the whole.
And perfectoid spaces, they sound too good to be true. Are they like the holy grail of non-Archimedean geometry?
Well, not quite the holy grail, but they're definitely a game changer.
Okay.
Because imagine like building a bridge between two islands that everyone thought were totally separate. That's what perfectoid spaces do. They connect these seemingly unrelated concepts in math, and they let mathematicians transfer ideas and techniques in ways that they just couldn't before.
So they're like the Rosetta Stone of math.
Exactly.
Unlocking new understandings by connecting these different mathematical languages.
Yeah. And the paper uses these really powerful tools to tackle some major challenges in math. It even addresses this conjecture by Pott and Hansen about duality in intersection cohomology.
Okay, break it down for me. Intersection cohomology. It's like looking at a cake and understanding not just the frosting on top, but also like all the layers inside.
Exactly. It's about understanding the internal structure of these really complex shapes.
Okay.
And how all the different parts kind of fit together.
Gotcha.
To form a whole.
Okay.
And this paper offers new insights into how Poincaré duality works in this setting.
Okay.
And it even uses these really cool examples to make it click.
Okay.
Like it compares smooth curves to their algebraic counterparts.
So it's like having a 3D model of a complex machine instead of just a flat blueprint.
Exactly.
You can really see how everything interacts and understand the system as a whole.
And the paper doesn't shy away from like getting into the weeds.
Okay.
Like it dives into these concepts of residue fields and valuations.
Okay.
What we talked about earlier, that redefine size and distance.
It's like realizing that the ruler you've been using your whole life has a completely different set of markings.
Exactly. And that's where things get really interesting, because now we can ask new questions that we couldn't have even imagined before.
So we're not just changing the tools, we're changing the entire game.
Exactly. And speaking of tools, the paper highlights another really important one called etal cohomology.
Etal cohomology. Okay, I'm going to be honest, that one sounds a little intimidating.
Yeah, it's a mouthful.
Is it going to require like a PhD in mathematics to understand?
No, not at all.
Okay.
We can break it down. So imagine using a special kind of light to illuminate an object.
Okay.
And this light reveals details that you couldn't see under normal light.
Interesting.
That's kind of what etal cohomology does.
Okay.
It lets mathematicians study spaces by examining their etal covers.
Etal covers.
Yeah, and you can kind of think of these as like special maps that preserve certain properties of the space.
So it's like using a special lens to examine a seemingly simple object, only to discover this like hidden world of complexity within.
Precisely.
Okay.
These etal covers reveal hidden information about the structure and the behavior of the space. It's like if you were looking at a city, but instead of just looking at it from street level, you could also see the underground tunnels, the power grid, the communication networks.
Suddenly you understand how everything's connected.
Exactly.
And how the city functions as a whole.
Yeah. And in this case, the city is our mathematical space.
Okay.
And etal cohomology is the key to like unlocking its secrets. And the paper goes deep into the specifics.
Yeah.
It introduces these concepts like list sheaves and trace maps.
Okay. Those sound interesting.
Yeah.
But how do those concepts help us understand the bigger picture of non-Archimedean geometry?
Okay, so imagine you're trying to understand the flow of water in a river.
Okay.
You might study its speed, its depth, the shape of the riverbed.
Right.
These are all local properties that change as you go down the river.
Right.
List sheaves are like mathematical snapshots of these local properties.
Okay.
They capture how things are behaving at different points in our space.
So it's like having a series of photographs taken along the river,
Exactly.
each one capturing a specific aspect of the water's flow at that point.
Yeah.
And you put them all together and you get a more complete picture of how the river flows.
Precisely.
Yeah.
And now imagine you want to understand how information is transported by the river.
Okay.
So this could be like pollutants or nutrients.
Right.
This is where trace maps come in. They help us track how information flows from one part of the space to another.
Okay.
So like tracking the movement of those pollutants downstream.
So it's like having sensors along the river that measure the concentration of pollutants at different points.
Exactly.
And the trace maps are like the data analysis tools.
Yes.
That show how those concentrations change over time and distance.
Precisely. And in the context of this paper, trace maps play a crucial role in understanding how information is moving within and between these rigid analytic spaces.
So we're not just like passively observing the flow of information in this non-Archimedean world.
Right.
This paper is actually giving us tools to like map it out.
Exactly. And it gets really in the weeds.
Okay.
Like constructing different types of trace maps, comparing them. We've got like algebraic ones, analytic ones, even ones called smooth source trace maps.
Okay.
It's like having all these different blueprints for navigating this space.
So this paper is giving mathematicians a practical toolkit for working with these concepts instead of just leaving them stranded with these abstract theories.
Exactly. And it's not even just presenting the tools, it's showing you how to use them.
Okay.
We see trace maps being used with those curve-like affinoid fields that we talked about. And within perfectoid spaces, it's very hands-on.
That's what I love about this paper.
Yeah.
It bridges that gap between theory and application because it's one thing to say, here's a new type of map.
Right.
But it's another thing entirely to say, and here's how you actually use it to navigate this like totally new territory.
Exactly. It's like giving you the map and then showing you how to use a compass with it.
And it goes even deeper than that, right? Because the paper highlights this like crazy compatibility between all the different types of trace maps.
Yeah, that's wild.
It's like discovering that whether you like hike or bike or drive through a forest, all the paths lead to the same clearing. So it suggests this like hidden unity. Like there's this fundamental underlying structure to all of this, regardless of how we actually approach it.
Exactly. And it really speaks to how elegant math is.
Right.
That all these different approaches, these different constructions, they're all tapping into the same truth.
Well, we've covered a ton of ground today, from the very mind-bending concepts of non-Archimedean fields and rigid analytic spaces to the intricate tools of ATEL, cohomology, and trace maps. This has been quite a journey.
And we've only just scratched the surface.
Right.
There's still so much more to explore in this paper and beyond it.
That's what's so exciting about this entire field of mathematics.
Absolutely.
It's like we've stepped onto the shore of this vast, uncharted continent. Who knows what we'll find as we go further into non-Archimedean geometry.
And this paper gave us a great map and compass to guide our explorations.
It really did. So for all of you listening out there, keep this thought in mind. What if everything we thought we knew about geometry was just the starting point?
Right.
What if the universe has these hidden dimensions, these unseen structures that are best understood through this lens of non-Archimedean geometry? This paper is inviting all of us to consider that possibility and to embark on our own journeys of discovery.
Absolutely.
Thanks for joining us for this deep dive.
Ever find yourself glued to that little blue dot on your GPS? Like, how does it actually know the fastest route?
Yeah.
Well, you can thank something called non-Euclidean geometry for that.
It's true.
It's a bit mind-bending, but this kind of math, it's key to everything from GPS to online security.
Absolutely.
And today we're taking you even deeper into this world with a research paper, and get ready for this title, Relative Poincaré Duality in Non-Archimedean Geometry.
Now, I know that title might sound a bit intimidating, but trust me, the ideas within, they're incredibly fascinating. We're going to unpack a whole new set of rules that govern a kind of hidden geometry.
Hidden geometry. Okay, that's really intriguing. But before we dive into the paper itself, can you give us a crash course on what makes non-Archimedean geometry so different from the geometry we're familiar with?
Sure. Imagine instead of measuring distance with a regular ruler, you have one with strange markings. And suddenly things aren't simply close or far anymore. This ruler, it operates under completely different rules, leading to some unexpected results that really challenge our everyday understanding of space. That's the essence of non-Archimedean geometry.
Okay. Okay, that's a really interesting way to visualize it. So how does this new way of thinking about distance, how does it play into the paper we're looking at today?
So this paper tackles a fundamental concept called Poincaré duality, but applies it to this unusual non-Archimedean world. It's a bit like discovering a secret passage that links different areas within this new geometric landscape.
I'm starting to see why this is so groundbreaking. But before we go any further, can we clarify some of the terms used in the paper? Words like rigid analytic spaces, adic cohomology, and of course Poincaré duality itself. I mean, they sound a bit like a foreign language to me.
Absolutely. Let's break those down. Think of rigid analytic spaces as the building blocks of shapes in this non-Archimedean world.
Okay.
Similar to lines and circles in regular geometry,
Right.
but with their own unique properties. Now, adic cohomology, that's like having a set of blueprints. But instead of for a building, it helps us understand the structure of these unusual spaces.
So if rigid analytic spaces are the building blocks and adic cohomology is the blueprint, where does Poincaré duality fit into all of this?
Poincaré duality is what reveals the fascinating connections between those blueprints and the building blocks. It's a powerful tool that helps mathematicians uncover hidden relationships and symmetries within these complex geometric objects. What this paper does is prove a version of Poincaré duality for a specific type of map. Think of it as a specific way to navigate these spaces, called smooth proper morphisms. It's a significant leap forward in the field of non-Archimedean geometry.
This is all starting to click now. We're essentially uncovering hidden connections within a system of geometry that operates under completely different rules than what we're used to. It's like we're explorers charting unmapped territory.
That's a great way to put it. And just like explorers, the authors of this paper are making some pretty remarkable discoveries.
So we're talking about uncovering hidden connections in this new geometric landscape.
Yeah.
What specifically makes the approach in this paper so innovative?
Well, one of the things that really struck me was how the authors use something called curve-like affinoid fields.
Okay.
Imagine trying to understand a complex 3D model.
Right.
But instead of looking at the whole thing at once, you have a tool that lets you isolate and analyze individual curves within the model.
Wow.
These fields, they act like that tool, allowing mathematicians to break down those rigid analytic spaces into smaller, more manageable pieces.
It's like they've invented a new kind of mathematical magnifying glass to examine the intricate details of these spaces.
Exactly. And what's even more fascinating is how the paper connects non-Archimedean geometry to other areas of math, like algebraic geometry and topology. It's like they're building bridges between seemingly separate mathematical islands, highlighting a deeper interconnectedness that we might not have noticed before.
That's what I find so exciting. It's not just about solving problems within one specific area of math.
But about revealing these hidden links that weave together different mathematical disciplines.
Precisely. And one of the key connections this paper makes is to something called relative duality theory. Now, bear with me here because it gets a bit technical.
Okay.
But essentially, this theory, it provides a powerful framework for understanding relationships in geometry.
Right.
What the authors do is build upon this framework and adapt it to the world of non-Archimedean geometry.
Okay.
It's like they've taken a powerful tool from one area of math and found a way to use it to unlock new insights in another. So they're not just exploring new territory, they're bringing new tools with them to help us understand it better. What would you say is one of the biggest aha moments a reader might have while going through this paper?
One of the biggest takeaways is that the paper doesn't just present solutions. It also acknowledges its limitations and points towards new avenues of research.
Okay.
For instance, they delve into the concept of perfectoid spaces, which have certain desirable properties in this non-Archimedean setting. They basically say, here's what we've learned about these spaces, but there's still so much more to explore. It's like they're inviting other mathematicians to join them on this exciting journey of discovery.
It's inspiring to see how this paper, it pushes the boundaries of what we know while also acknowledging there's still so much more to learn.
Right.
But for those of us who aren't mathematicians, what are the key takeaways? What makes this research truly significant?
You know, that's a question I always ponder myself. Like, how does this seemingly abstract math connect to the real world? In this case, proving a new version of Poincaré duality in the non-Archimedean setting, It has potentially huge implications.
Okay.
It's like finding a missing puzzle piece, and then suddenly it connects two previously separate puzzles.
So it's about more than just proving a theorem. It's about opening up new possibilities for mathematical exploration.
Exactly. Take cryptography, for example.
Okay.
This field relies heavily on complex mathematical structures
Right.
and non-Archimedean geometry with its unique properties.
Yeah.
It offers a whole new way of approaching these structures.
Okay.
This paper, by deepening our understanding of these spaces, could pave the way for new and more secure cryptographic methods in the future. It might sound like a reach, but remember, the security of our online transactions, it relies on number theory, a branch of mathematics that was once considered purely theoretical.
So while we might not see immediate applications of this research in our daily lives,
Right.
it has the potential to shape the future of fields like cryptography in profound ways.
Precisely, and beyond specific applications.
Yeah.
This paper highlights the interconnected nature of mathematics itself.
Okay.
It encourages us to look for connections between seemingly disparate areas of study, and that's where true innovation often lies.
It's like that saying, all roads lead to Rome, except in this case, it's all mathematical roads lead to interconnected discoveries.
I like that. And who knows what other hidden pathways mathematicians will uncover as they continue to explore this fascinating world of non-Archimedean geometry.
Well, I have to say, this deep dive has definitely expanded my mathematical horizons.
Good.
We started with a simple GPS, and we ended up exploring the intricate structure of non-Archimedean spaces.
It's been a pleasure guiding you through it.
And for our listeners, thank you for joining us on this intellectual adventure. We hope you've gained a new appreciation for the power and the beauty of mathematics, even when it delves into these abstract realms. If this deep dive has sparked your curiosity, don't be afraid to delve further into the world of non-Archimedean geometry. There are amazing resources available online, and who knows, maybe you'll be the one to make the next groundbreaking discovery. Until next time, keep exploring and keep asking those what-if questions.
Welcome to the deep dive. We love digging into fascinating research papers, finding those aha moments, mind-blowing connections, the stuff that makes you go, whoa! And today, we're diving into a world where geometry gets a little weird, non-Archimedean geometry.
It's like, imagine trying to measure something, but the usual rules just vanish.
Yeah.
Like measuring distance in a dream.
Okay, yeah, things get a little fuzzy there. But luckily, we have this paper to guide us. Relative Poincaré duality in non-Archimedean geometry.
Right off the bat, this paper throws us into the deep end with something called Poincaré duality. Picture a mirror, but instead of just reflecting shapes, it shows you hidden connections within those shapes.
Ooh, I like it, a trippy funhouse mirror. So where does this mirror fit into the non-Archimedean world?
This paper explores Poincaré duality in something called rigid analytic spaces. Sounds a bit technical, but trust me, they're built on non-Archimedean fields. These fields are like alternate realities for numbers, completely changing the game.
Okay, my brain's already bending a bit. Before we get lost in space, can we break down these non-Archimedean fields? What are they, really?
So think about our normal numbers. Two numbers are close if their difference is small, right? Well, in non-Archimedean fields, closeness is about divisibility by a prime number. It's not about the size of the difference, but if a specific prime number divides into it.
Whoa. So it's not about big or small, but whether a certain prime number fits in neatly? That's wild.
Exactly. It totally changes how we think about distance. A cool example, p-adic numbers. They're used in cryptography, which keeps our online stuff secure.
Hold on, so this isn't just some abstract math theory. It has real-world uses. Now I'm really interested. But how do we even start studying these rigid analytic spaces? They're built on this totally different number system.
That's where curve-like affinoid fields come in. Imagine them as special measuring sticks for these spaces. They're the key to navigating this new world.
So our normal rulers are useless, and these curve-like ones are the new tools of the trade.
Exactly. And get this, they have these fascinating properties, especially when you zoom in on them mathematically. The paper looks at what happens when you have a finite extension of these fields, like looking at a fractal. The patterns repeat at different levels.
So instead of getting simpler as we zoom in, things get more complex. Okay, this paper also mentions something called an analytic trace map. Light it up for us. What's that all about?
Picture a map, but it not only shows the landscape, It reveals hidden tunnels connecting distant places within these rigid analytic spaces.
Yeah.
It's a bridge between different parts of this strange world.
Okay, now this is getting really cool. Bizarre spaces, new ways to measure, and a map with secret passages. How do they even begin to understand this trace map?
They give us two ways, actually. One uses torsors, which are like mathematical bundles that help organize info. The other uses formal models, like blueprints for these abstract spaces. Imagine navigating with a compass and map versus using GPS.
I'm starting to see how this all comes together. It's like we're building a toolkit to explore uncharted territory. But let's not forget, the big goal is proving Poincaré duality in this new world. It's like a Rosetta Stone, translating between different types of information and unlocking deeper understanding, right?
Exactly. It's about finding hidden connections. And that's where it gets even more interesting. They dive into Poincaré duality with something called Zariski constructible coefficients.
Coefficients sounds a tad technical, even for us. Are we talking like adding layers of complexity to an already complex thing?
You got it. Think of our maps of these spaces. We're going from basic outlines to filling them in with colors, textures, the whole shebang. These coefficients are those extra details, helping us study even more intricate shapes.
So instead of a simple sketch, we've got a high-definition, super detailed satellite image, much clearer picture.
Exactly. And Poincaré duality still works with this extra complexity. That's how you know it's a powerful concept, like a law of nature, unbreakable.
This is all mind-blowing math, but be honest. Does any of this matter in the real world? Or even other areas of math?
Absolutely. This links directly to periodic Hodge theory, which is super hot right now in the math world.
Ooh, okay, I'm listening. Periodic Hodge theory. Tell me more.
Imagine a crazy jigsaw puzzle, but the pieces are scattered across different dimensions, each with its own rules. Periodic Hodge theory finds the way to connect those dimensions, see how the pieces fit together across different mathematical universes.
So this paper isn't just about Poincaré duality, it's building bridges to number theory, algebraic geometry. It's all connected.
Exactly. And speaking of connections, they also touch on a prediction by Bott and Hansen about intersection cohomology.
Okay, that one sounds a bit intimidating, even for me. What is that, and why should we care?
Imagine studying the shape of something with rough edges, sharp points, places where geometry gets wonky. That's a singular space. Think cube versus a sphere. The cube has those sharp corners. Intersection cohomology helps us understand the geometry of those weirder shapes, even the tricky spots.
So special geometry for handling the weirdness. Count me in.
And here's the kicker. This paper shows that Bott and Hansen's prediction about intersection cohomology. It holds true in this non-Archimedean setting too. Proof that this research matters on a bigger scale.
It's amazing the depth here, connecting all these seemingly different ideas.
It shows how elegant and interconnected math truly is. But I love how they wrap up, leaving us with a lingering question.
Ooh, a good cliffhanger. What's the final thought?
Remember those lissy sheaves, those smooth coatings we talked about? Well, they ask, what if we relax that condition, allow for rougher, more complex coatings, more like the real world? Does Poincaré duality still hold up then?
So after this wild ride through this mind-bending world, just when we thought we were getting a handle on things, they've opened the door to even more complexity.
Exactly, an open invitation to dive deeper for anyone intrigued by these mysteries.
They're practically daring us to pick up where they left off. We showed you the basics, now go explore the really wild stuff.
That's what makes this kind of research so exciting. Answering questions, but also uncovering a whole new set of mysteries.
It's like that feeling when you get deep into a subject and realize how much you don't know. This whole dive has been a trip through mathematical wonderland.
And like any adventure, it's the journey, right? Those aha moments, the expanding understanding. That's the good stuff.
Speaking of, I was really struck by how they connected these super abstract ideas to real-world stuff like cryptography. Never thought non-Archimedean geometry could be so practical.
It's what I love about math. It seems abstract at first, but then you find these amazing connections to other fields, even the world around us.
Totally. This deep dive definitely opened my eyes to this whole other side of geometry. I'll admit, a little intimidating at first, but you broke it down so well.
Appreciate it. Always fun to share these ideas and get people curious. Who knows, maybe one of our listeners will take on that challenge, explore Poincaré duality in even weirder settings.
That would be awesome. Even if they don't revolutionize the field, just engaging with these ideas, stretching those brain muscles, that's a win in itself.
Absolutely. So to everyone listening, remember, curiosity is key. Dive deep into whatever grabs you, even if it seems tough at first. You never know what you'll discover.
And who knows, maybe we'll see you back here on the deep dive, ready to tackle another research adventure. Until then, keep those minds curious.
Ever feel like, I don't know, our everyday way of thinking about distance is just not like the whole picture?
You mean like there's a different way to measure how far apart things are?
Yeah, exactly. And that's actually what we're diving into today, this whole other way of looking at geometry. Non-Archimedean geometry, they call it.
And it gets, well, let's just say it gets a little weird.
Weird in the best way possible, right? At least that's what I'm hoping. We're tackling this research paper today. It's called Relative Poincaré Duality in Non-Archimedean Geometry. And honestly, it's pretty next level stuff.
It's definitely a brain bender, but it's doing really important work, like changing how we think about shapes in these really unusual spaces.
The researchers are kind of like pioneers then.
Yeah, exactly. And they've got some big names backing them up too, like the National Science Foundation and the Institute for Advanced Study. They're involved.
Wow, okay, so this is legit groundbreaking research we're talking about.
It really is.
So before we get too far into the weeds, can we, I don't know, maybe back up a bit? Like, what are some of the main things we're going to run into in this non-Archimedean world?
Well, imagine instead of measuring with a ruler, you're measuring by how many times you can, say, divide something by a specific number.
Okay, that's already bending my brain a little.
Right. And instead of points and lines like we're used to, we're dealing with things called affinoid fields and valuation rings.
So it's less about, like, actual length.
Yeah.
And more about, what, levels of divisibility or something.
Yeah, you've got it. Like, think of affinoid fields as the, I don't know, the ingredients of our mathematical recipe. And then the valuation rings, those are like our measuring tools. They tell us about the divisibility of those ingredients.
Okay, I think I'm starting to see how this gets really complex really quickly. But the researchers, they're using these ideas to actually study shapes, right?
You got it. Specifically, they're looking at how curves and surfaces, those basic 1- and 2-dimensional shapes, how they act in this whole different non-Archimedean system.
And they use this thing called universal compactification to study them. It sounds intense.
It is, but in a really cool way. Imagine taking a line that goes on forever and bending it so it makes a circle. You're making something infinite finite.
Whoa.
Yeah, and that's kind of what compactification does, just obviously way more complicated. It's like they're putting these shapes under a microscope.
And even when you're dealing with abstract math, you still need some kind of framework, right? They use formal models for that.
Exactly. Think of them like blueprints or those little model kits people build. They give mathematicians a concrete way to actually work with these shapes we're talking about.
Yeah, like this is usually where I start feeling lost, but you're making it strangely fascinating. What about this trace map idea, though? I keep seeing that pop up.
So what's wild is how mathematicians can move between different dimensions in these spaces, right? And that's where the trace map comes in. It's like a tool that lets them go from these really complex calculations in higher dimensions down to simpler ones in lower dimensions.
So they're like simplifying things.
In a way, yeah. They're finding ways to make the math more manageable without losing the important information.
So did they find a new way to use that tool, the trace map?
They did. They found these really elegant ways of calculating it in certain situations, which is a huge deal. Like finding a shortcut in a maze, it opens up all kinds of possibilities.
That's like finding a secret passage in a library or something, right? Suddenly you can access information in a completely new way.
Exactly. And that's leading to a better understanding of a really fundamental idea in math called Poincaré duality, which is basically this really cool principle. It shows this like hidden symmetry in math between different ways of looking at a shape, how we understand its shape.
Okay, so like a mirror image, but way more complex, I'm guessing?
More like a secret handshake, yeah. Like finding out that two ideas that seem totally unrelated are actually like deeply connected.
Intriguing. But how does that work with these non-Archimedean spaces? I mean, distance itself is different there.
And that's what's so exciting. This research, they proved a new version of Poincaré duality, and it works even in these really weird spaces. Like, imagine discovering a law of physics, but in a whole other universe.
So not just some abstract math thing, it could actually change how we see these big concepts in all different parts of math.
Totally. It's like finding this hidden passage that links continents together. It could mean big breakthroughs in areas we haven't even thought about.
My mind is officially blown. See, this is why I love these deep dives. But before we go too far down the rabbit hole, can we go back to that trace map thing for a sec? What kind of problems does it actually help solve with this research?
So one of the coolest things about this research is how they use trace maps to understand how curves and surfaces, those basic shapes, how they relate to each other in non-Archimedean geometry. Remember how we talked about going from higher dimensions to lower dimensions?
Yeah, like that mathematical elevator you were talking about?
Exactly. Well, here they're using the trace map to see how information about a surface can basically be projected onto a curve, and that gives them clues about the geometry of both.
So it's kind of like, I don't know, shining a light through a sculpture, and then you can study the shadows it makes.
Yes, exactly. And what they found is that those shadows, the projections from the trace map, they tell you a lot about the geometry of these non-Archimedean spaces.
Okay, this is where I usually just nod along, but I'm actually really curious. What kind of information are we talking about? What can they actually figure out from those projections?
Well, for example, they can learn about the genus of a surface. Basically, how complex it is, like how many holes it has. Think about the difference between a donut and a basketball.
Okay, a basketball has no holes, a donut has one. Makes sense.
Right. So using the trace map, they can figure out the genus and other important properties just from those lower dimensional projections. It's like they have X-ray vision for these shapes.
It's like those optical illusions where you see one thing, but then it's actually something else too.
Yeah.
So they're seeing both the higher and lower dimensions at the same time.
Kind of. And the crazy part is, these discoveries in non-Archimedean spaces, sometimes they can even be applied back to our regular geometry. It's like finding a new rule in a parallel universe and then realizing it affects ours too.
Okay, now you're really blowing my mind. This is way more than just measuring things. So all this to say, what could this actually be used for in the real world?
This specific research is very theoretical, but the methods they used could have a big impact in a lot of fields. Like non-Archimedean geometry is already being used in cryptography, keeping online communication secure.
So my online banking is safe thanks to these non-Archimedean explorers. Good to know.
Well, it's not quite that direct, but you get the idea. The point is, even these super abstract math concepts, they can have real-world uses. Even in physics, like string theory, it's being used to understand, like, the fabric of the universe.
Wow, okay. From safe transactions to the nature of reality. That's some powerful math. Did the researchers mention any specific future applications in this paper, though?
They did mention that their work could be useful in something called Oraculov theory.
And without making my head explode, can you explain that a little?
So imagine trying to combine regular geometry with number theory, which is all about whole numbers and their relationships. Oraculov theory, it's like building a bridge between those two.
So it's like a common language for two different parts of math.
Yeah, exactly. And these findings on Poincaré duality, the researchers think it could lead to new tools and understanding within Oraculov theory.
So even more connections and mysteries to uncover. Now, I know we've been talking about some pretty high-level concepts, but even the most complex math, it usually boils down to solving very specific problems, right? What are some of the problems this research helps to address within non-Archimedean geometry itself?
A big challenge has been finding good ways to actually calculate these trace maps. They can be really hard to work with. This paper gives some really elegant solutions, though, at least for certain cases, which is huge.
So they've made a better map of this uncharted territory.
Exactly, and not just a map. They've given us tools to navigate it, too.
And now other mathematicians can use those tools to explore even further.
Yes, and that's what's really exciting. It's not just answering old questions, it's opening up new ones. Like they've given us a whole new way to look at the world of math.
I love that analogy. Speaking of new ways of looking at things, did the researchers give any hints about what they're planning to explore next in this non-Archimedean world?
They didn't give too much away, but they did mention some limits to what they understand right now. Like, their proof for Poincaré duality, it only works for a certain kind of non-Archimedean space.
So they've charted one continent, but there's a whole world out there still.
Exactly. And they even hinted that there might be even more powerful techniques out there just waiting to be discovered, especially when it comes to trace maps.
I have a feeling those future discoveries are going to be amazing. But before we get totally lost in the weeds, what's the one big takeaway our listeners should remember about this research? I think the main takeaway, if I had to pick one, is that even in math, which seems like, I don't know, it's all figured out, there are still mysteries to solve.
Totally. And this research shows how exploring those mysteries can lead to connections you'd never expect and really deep insights.
It's like, those old maps that say, "Here be dragons." Mathematicians are out there exploring those blank spaces, and sometimes they They find something amazing.
And sometimes those discoveries are way more important than anyone could have guessed.
Speaking of which, what about the paper itself? Was it a tough read, or did they at least try to make it interesting?
Well, it's a very technical, not exactly like beach reading,
Yeah, I figured.
But one thing I did like was how they used really vivid language, even analogies, to explain these tough concepts.
Oh, yeah. Like what?
So, for example, when they talk about certain points in these non-Archimedean spaces, they call them boundaries. It helps to actually picture these abstract things.
It's like they're giving you a hand up this mathematical mountain we're climbing.
Exactly. Like breadcrumbs. But instead of leading to a gingerbread house, they lead to a deeper understanding of the math itself.
I like that. And it shows they're not just messing around with numbers in isolation. This stuff actually connects to the bigger picture, right?
Exactly. And that's what's so cool about this research. It's not just about proving one thing. It's about expanding how we see the whole mathematical universe, how it all fits together.
Well, you've definitely expanded my understanding today. I feel like I've taken a crash course in non-Archimedean geometry, and wow, it is pretty mind-blowing stuff.
It's amazing stuff, and who knows what else is out there waiting to be discovered as mathematicians keep pushing the limits.
Maybe one day we'll be able to visit these spaces in virtual reality or something.
Now that would be something. But even without VR, what we learn from this kind of math, it could really change how we see the world around us.
That's a great point. So for anyone listening who wants to learn more, where should they start? Besides this paper, I mean, obviously.
But there's actually some really good stuff online for beginners. Just search for, like, non-Archimedean geometry for beginners, and you'll find some good starting points.
Perfect. And with that, I think our deep dive has come to an end. My brain is officially full, but in a good way.
It's been great exploring this with you.
And to everyone listening, until next time, stay curious, keep asking questions, and never stop exploring all those fascinating corners of knowledge. All right, let's jump into the world of non-Archimedean geometry.
It sounds a bit intimidating, right?
It does sound pretty complex, yeah. We've got these excerpts from a paper called Relative Poincaré Duality in Non-Archimedean Geometry.
Yeah, it's a mouthful.
It is. And the concepts seem pretty out there, even for mathematicians, I'm guessing.
Oh, absolutely. Some of this stuff has been puzzling mathematicians for, like, decades.
So where do we even begin? I mean, what is non-Archimedean geometry?
Okay, so imagine, like, throwing out the geometry you learned in high school.
Out the window.
Yeah, forget those straight lines and perfect circles.
No more protractors.
Exactly. In non-Archimedean geometry, the way we measure distance, it doesn't work the way we're used to.
Okay, so things get a little funky.
A little, yeah.
But this isn't just some, like, mathematical curiosity, right? I mean, there's a reason mathematicians are so interested in this stuff.
Right, because it turns out that this weird abstract geometry, it actually pops up in other areas of math, like number theory, for example.
Number theory, okay.
Yeah, like think about prime numbers.
Okay.
Trying to understand how they work.
Right.
Non-Archimedean geometry can actually give us new insights into those kinds of problems.
It's like a secret passage, kind of.
Yeah, like a secret tool that helps us unlock these other mathematical mysteries.
That's pretty cool, all right?
Yeah.
So this research paper you're looking at, it's like venturing further down that secret passage.
Exactly. It's like we're pushing the boundaries even further.
Okay, so the stakes are high, the concepts are mind-bending. I'm ready. Let's dive in.
Let's do it. To really understand what's going on in this paper, we need to start with this idea of Poincaré duality. Have you heard of that?
Ah, yes, the duality with a fancy French name. It's like trying to understand a sculpture, but you can only look at its shadow.
You're on the right track. So imagine trying to figure out the shape of something, but you can only see its outline from different angles, right?
Right.
Poincaré duality, it's kind of like that. But instead of shapes and shadows, we're dealing with like these really abstract spaces, much harder to visualize.
So like a mathematical X-ray vision.
Yeah.
I like it. Okay, I'm following so far.
Very good.
Now, one of the things I found really interesting about this paper is that it proves the existence of something called, what was that, trace map, right?
Yeah, that's a big one.
In certain non-Archimedean settings.
Exactly.
So what exactly is a trace map and why is it such a big deal?
Okay, so imagine you have like a signal, a pulse of light maybe, traveling through this like incredibly complex network.
Okay, I'm picturing it.
A trace map, it's like this tool that lets you track that signal as it goes through all these twists and turns across different spaces.
Even in this weird non-Archimedean world we're talking about.
Exactly, even there. So it's a way to follow the signal, see where it goes, even when things get really strange.
So they've basically created a map for this uncharted territory.
Yeah.
That's impressive.
It is, and you know it's even more impressive.
What's that?
They actually found 2 ways to prove this trace map exists. 2 different approaches, which is like a testament to just how clever these mathematicians are, right? Like finding 2 different paths that lead to the same incredible view.
Wow, so it's not just about the destination, but the journey and the different perspectives you gain along the way.
Exactly. And speaking of different paths, this paper also dives into these things called, get ready, curve-like affinoid fields and henselized completed residue fields.
Ooh, okay, those sound a little intimidating.
Yeah, they're a mouthful, for sure.
Can we stick with our analogy here? We were talking about signals traveling through a network, right? So if those signals are, like, dancers, and the cycle classes mentioned in the paper are the steps and patterns of the dance,
right,
then what are these fields?
Okay, I like where you're going with this.
It's the best I got.
No, it's good. So in this dance floor analogy, those fields are like, they're like specific areas on the dance floor, each with its own little set of rules.
So they're essential for understanding the nuances of the dance, the movements within this larger space.
Exactly. And much like a choreographer might use a variety of steps and formations to create a dance, the researchers use these fields as tools to navigate the complexities of non-Archimedean spaces and arrive at their proof.
So they've set the stage, they've got their tools, they've got their maps. What did they find?
Well, before we get to their findings, we need to delve a bit deeper into the conjectures themselves, because proving them unlocks a few other mysteries within this world of non-Archimedean geometry, and the implications go even further than that.
Okay, so it's a chain reaction of mathematical discovery. Tell me more.
Okay, so one of the conjectures they tackled has to do with how these trace maps, the ones we talked about earlier, actually behave.
So we're going deeper into their function, not just their existence.
Precisely. The paper takes a deep dive into how these trace maps operate within these specific non-Archimedean settings.
Okay.
Specifically, they were laser focused on something called relative Poincaré duality.
Right, the X-ray vision. So this is where it all comes together.
You got it. By proving this conjecture about trace maps, they were able to confirm that this X-ray vision, this ability to understand complex spaces by looking at simpler projections, actually works the way we thought it did within these specific non-Archimedean settings.
Okay.
And that's huge because it validates a lot of the assumptions and tools that mathematicians have been using in this field.
It's like they've reinforced the foundations of a whole branch of mathematics.
Exactly. And that's incredibly valuable because it means we can be more confident in our explorations of this world. But what's even more exciting is that it opens up a whole new set of questions and avenues for research.
Like what? Give us a taste of the mysteries yet to be solved.
Well, one question that immediately comes to mind is, could these results on trace maps be extended to even more general settings within non-Archimedean geometry? The spaces they focused on in this paper, while complex, are still relatively specific. What happens if we try to apply these ideas to even wilder, more abstract spaces?
It's like they've opened a door to a whole new wing of this mathematical mansion, and we're just starting to peek inside. What else? What other mysteries are hidden in this new wing?
Well, remember how we talked about those curve-like affinoid fields and how they act like specific areas on the dance floor?
Yes, I remember.
Well, the researchers primarily focused on how these trace maps work within those specific areas. But what about the transitions between those areas? What happens when those signals we talked about earlier cross those boundaries?
Ooh, that's a great question. It's like we're asking how the dance steps change as we move from one type of music to another.
Exactly. And that's just one of the many unanswered questions that this research opens up.
Wow.
This paper has essentially given us a flashlight and a map for a small portion of this vast, uncharted territory, but there's still so much more to explore.
This is so cool. It's like we've been given a glimpse into the cutting edge of mathematical research.
And it's a reminder that mathematics is a living, breathing field, constantly evolving and pushing the boundaries of what we know.
You've definitely made me want to learn more about non-Archimedean geometry.
Really?
I mean, who wouldn't be intrigued by spaces where distances behave in such unexpected ways?
It's a truly fascinating area, and this paper is just one example of the incredible work being done in this field.
Well, I think it's safe to say that this deep dive has been a resounding success. We've taken a dense research paper, distilled its key findings, and explored the implications of this groundbreaking work.
And we've done it all with a healthy dose of analogies and enthusiasm.
Exactly. Because even the most abstract mathematical concepts can be made accessible and exciting when you have the right guides.
Absolutely.
So before we wrap up, what's the one takeaway you'd like our listener to ponder?
I think the most important thing to remember is that mathematics is not just about formulas and equations.
Okay.
It's about exploring new ideas, challenging our assumptions, and pushing the boundaries of human understanding.
I like that.
Non-Archimedean geometry, with its strange spaces and unexpected connections, is a perfect example of this spirit of exploration.
Beautifully said. So to our listener, we encourage you to keep that spirit of curiosity alive.
Yes.
Explore, question, and never stop learning. Because the world of mathematics, like the universe itself, is full of wonders waiting to be discovered.
And who knows, maybe someday you'll be the one pushing the boundaries of non-Archimedean geometry or some other equally fascinating field of mathematics.
Until next time, keep diving deep. I love that image of unanswered questions marking new trails on this map of non-Archimedean geometry.
It really drives home that even a major discovery like this is just one step on a much longer journey.
Definitely.
There's always more to find.
Speaking of the road ahead, I'm curious, did the authors give any hints about where this research might go next? Did they mention any specific areas where they believe their findings could be applied or expanded upon?
They did. Remember how we talked about the possibility of extending their findings about trace maps to more general settings?
Yeah, like moving from those specific areas on the dance floor to understanding how the transitions between different dance styles work.
Exactly. Well, in their conclusion, the authors actually suggest a few potential avenues for future research in the paper, focusing specifically on more general non-Archimedean spaces.
So they're basically saying, hey, we've shined a light on this one little corner, but there's a whole universe out there waiting to be explored, huh?
That's a great way to put it. And they even hint at the possibility of connecting their work to another area of mathematics called homological algebra,
Okay.
which adds a whole other layer of complexity that we haven't even touched on today.
Wow, the deeper we dive, the more there is to see, huh?
That's the beauty of it, right? Each answer leads to more questions. Each discovery opens up new paths to explore.
It's pretty incredible. Well, I think we can all agree that this deep dive has been a success.
I'd say so.
We've taken this really complex research paper, broken down its key findings, and explored just how groundbreaking this work really is.
And hopefully spark some curiosity in our listeners along the way.
Absolutely. So to everyone listening, don't let that curiosity fade.
Keep asking those questions.
Keep exploring, keep diving deep into the amazing world of mathematics.
Until next time.
Until next time.